We already mentioned the idea of exponential growth being that very, very rapid growth because exponential functions can approach positive infinity incredibly quickly. And that happens with a function like f of x equals 2 to the x power. This is an example of exponential growth because as we read that curve from left to right, we see an increasing pattern. Exponential functions can also take on a decreasing pattern there, though, like we see in the case of this curve in green. This is a function of the form, this is the function g of x equals 2 to the negative x power. So as it turns out, the coefficient of x in an exponential function is the growth rate for that exponential function. In the case where the growth rate, that coefficient in front of x, is positive, it means we see exponential growth. And in the case where that value is less than 0, we see what we refer to as exponential decay. Keeping that information in mind, we can look at example 2, where we're asked to determine whether the functions below could model exponential growth or decay, and then we want to identify the growth rate. In example 1, we have the function m of x is equal to 10 to the 8x power. We want to pay attention to that coefficient for x. Since that's something positive, this function could model exponential growth. Because that coefficient of 8 is greater than 0. And in part B, we have w of x equals 7 times 3 to the negative 6x. We still want to pay attention to that coefficient for x, which in this case is negative. So this function could model exponential decay because negative 6 is less than 0. And in each case, that value that we compare to 0 is the growth rate for the function. So for m of x in part A, our growth rate is 8. And for w of x in part B, our growth rate is negative 6. With again a positive value being linked to exponential growth and a negative value being linked to exponential decay.